Okay, this section is all about integrating trigonometric functions. Now, in some sense, we can already integrate a lot of different trigonometric functions, and it's probably a good idea if we actually just look at those right now. So, antiderivative of sine of x is, of course, negative cosine of x, and the antiderivative of cosine of x is, of course, sine of x. All right, and the antiderivative of tangent of x is ln of absolute value of secant of x. And you can establish this by writing sine over cosine and then doing a u substitution, and that's going to work. Okay, there's a few more. We know the antiderivative of secant squared of x is tangent of x, of course. We know the antiderivative of cosecant squared of x is negative cotangent of x. And there's a couple other freebies here. We know the antiderivative of secant times tangent is secant of x. And we know the antiderivative of cosecant times cotangent is negative cosecant of x. Okay, now what's conspicuously missing from this list? Well, several things. First of all, antiderivative of cotangent isn't on this list. Okay, but we can recover that one the same way. We integrated tangent. We'll write this guy as cosine over sine. We will let u equal sine of x. So du is cosine of x dx. This changes our integral to du over u, which integrates to ln of absolute value of u. And so our final answer, which is the antiderivative of cotangent, is ln of absolute value of sine of x plus c. Here's another one that's missing from the conversation. Antiderivative of secant. Well, this one has a very interesting trick. So I'm never going to ask you to repeat this trick, but it's important that you see it once. So the move is that we multiply by 1, but a very special version of 1. We're going to multiply by secant of x plus tangent of x divided by secant of x plus tangent of x. So what do we get in the numerator? We get secant squared of x plus secant of x tangent of x. And in the denominator, we still have our secant of x plus tangent of x. Now we're going to use a u substitution, and we're going to note that the numerator of this giant fraction is exactly the derivative of its denominator. Imagine that. So we're going to let u be the denominator, secant of x plus tangent of x. So du is the derivative of secant, which is secant times tangent, plus the derivative of tangent, which is secant squared of x. That entire quantity is being multiplied by dx. And so our integral becomes all of that is du over u, which of course integrates to natural log of absolute value of u plus a constant. And so our final answer is that the antiderivative of secant is ln of the absolute value of secant of x plus tangent of x. So that you don't have to go through this process every time you integrate secant, it is definitely worth knowing the antiderivative of secant is ln of secant plus tangent. And finally, antiderivative of cosecant of x is actually, by a similar process, the negation of the antiderivative for secant, but with each of the functions replaced by their cofunctions. So secant gets replaced by cosecant, and tangent gets replaced by cotangent. And there we are. Oftentimes, I've seen this on tables of integrals. And this is equivalent. So ln of cosecant of x minus cotangent. So whichever you prefer. I actually prefer the first one because I feel it's a little more parallel with the version for secant that we use above it. And it's consistent with how calculus has been paired off with trig functions. For instance, the derivative of secant being secant tangent, the derivative of cosecant being negative cosecant cotangent. Okay, so among these two here and all of these guys, we have all the trigonometric integrals we're going to need to get through this section. Now, what's this section about? Well, you're going to see in the examples that we're going to start mixing and matching these trig functions and raising them to various powers and wondering, how do we integrate? For example, how do we integrate cosine cubed of x? Yeah, let's go right into that one. Okay, so with a few very notable exceptions, the general strategy for approaching trig integrals like this is going to be roughly the same. The idea is going to be that we want to do a u substitution, and we want to let u equal a trig function, and it won't be cosine, but we want to let u equal a trig function whose derivative already appears somewhere in here. So, of course, that would mean probably letting u equal sine in this case. But we don't have any sines in here directly. But if you think about trigonometry, we really do, because you can turn trig functions into other trig functions at will. So, well, what's going on here? Well, let's reserve the derivative of sine, which is cosine. So what I mean by reserve is we've got our cosine cubed, which we're going to write as cosine squared times cosine dx. And we're going to just call this guy our reserve. So this is reserved for our du, which means we're anticipating letting u equal sine. So that means that everything else we need to convert to in terms of sines. Okay, well, great. We know that cosine squared is 1 minus sine squared. So this is like the integral of 1 minus sine squared of x times, and then what we had reserved is our cosine x dx. So now we can let u equal sine of x, and hopefully you can see this is victory condition here. Du is cosine x dx, which is exactly what we had reserved. So our integral becomes 1 minus u squared. Cosine x dx is du. Well, now it's just a polynomial integral, so we can just walk through left to right and integrate each piece. So here we have u minus 1/3 u cubed plus our constant. And of course, u was sine of x, so we get sine of x minus 1/3 sine cubed plus our constant. Final answer. All right, well, this one looks a little more complex than the previous example, but it's really not much more difficult at all. The idea is we're going to reserve a factor, like before, either sine or cosine, which will be the derivative of our u substitution. Now, here, there is only one good choice among sine or cosine, and that is to reserve sine. And I'm going to explain when we're done this problem why that's the only good choice. So we're going to reserve a sine of x to go next to dx. So that means that our sine of the fifth power is now a fourth power. We've got this cosine that's just patiently sitting here. And we have one more sine factor that we moved all the way over here. And this is our reserved for du part. So if we're reserving sine x dx to be our du, that means that we must be letting u equal cosine. So everything over here needs to convert to cosines. Okay, so no problem, because sine to the fourth, we can use a Pythagorean identity for that. So sine to the fourth power is, in fact, sine squared squared. The cosine is already in terms of cosine, so we'll leave it alone. Sine x dx, we'll leave that over there. So now we can say, well, this is 1 minus cosine squared. That's all squared. That's multiplied by cosine to the fourth power. And here's our sine x dx. So we're ready to do our u substitution. Let u equal cosine. So our du is negative sine x dx. Perfect. We have a sine x dx. There will be a residual negative. No problem. We'll just throw it in front of the integral. And our integral converts to 1 minus u squared, which as a quantity is being squared, multiplied by cosine to the fourth, which becomes u to the fourth, and our sine x dx, which is negative du, but we've got our negative in front already. So there we are. And this is just a polynomial integral. So we should probably FOIL this thing. So 1 minus 2u squared plus u to the fourth, and that's all being multiplied by u to the fourth, which needs to distribute. So we have u to the fourth minus 2u to the 6 plus u to the 8 du. And we are ready to integrate, but why don't we just distribute the negative and write this in descending order. So we have negative u to the 8 plus 2u to the 6 minus u to the 4 du. Okay, lovely. Now we can integrate this thing. So this is going to be negative 1/9 u to the 9 plus 2/7 u to the 7 minus 1/5 u to the 5 plus our constant. And we're just about done. We just need to remember that u is equal to cosine. So this is negative 1/9 cosine to the 9th power x plus 2/7 cosine to the 7th power x minus 1/5 cosine to the 5th power of x plus our constant. Final answer. Okay, when we were first getting started on this problem, one of the things I said was that there's only one good choice for reserving with dx, and that was choosing sine of x, not cosine. So what if instead of reserving the sine of x dx and intending to let u equal cosine, as we did and successfully solved the problem, what if instead we reserved a cosine of x, like the very first example, and intended to let u equal sine? Certainly we could take cosines and turn them into sines just as easily as we could take sines and turn them into cosines, right? Well, not so fast. Let's see. If we reserved a cosine, we would have sine to the 5th times cosine now cubed, and then here's our reserve, right? Which means that we're intending to let u equal sine of x, so that our du is cosine of x dx. And that means that we'd have to convert to only involve sine of x's there, so that would be a big mess of powers of u over there on the left. There's an issue because cosine is to an odd power. So as long as you have an even power that you're trying to convert, as we did here with sine to the 4th, which became sine squared squared, well, that's really easy to convert using a Pythagorean identity. But if you're trying to convert an odd power, it's not impossible, but it's likely that once you're done converting that over into sines, you're going to get a really messy integral that's probably no easier than whatever you started with. And we have a better method for handling that situation. So remember, this is when you're trying to convert an odd power of sine or cosine after you've already made the reservation. Before you've made the reservation, it's actually good to have an odd power because you know you're going to make the reservation, which will leave you with an even power, which is why in the first example we did cosine cubed, and that was fine because we reserved one factor of cosine, and that left us with an even power of cosine, which was easy to convert over to sine. And in this example, we had an odd power of sine, and that's what we ended up reserving is one of the sine factors, leaving us an even number of the sine factors, which became easy to convert to cosine. Okay, but what if you only have even powers? Well, let's look at our next example. Okay, so here we want to integrate sine squared of x dx. Now, our move where we're reserving a factor of sine and converting what's left to cosines isn't going to work so well, because if we reserve a factor of sine, we'll only have one sine left, and that's difficult to convert to cosine. For instance, if we were to do that, we'd have sine of x times sine of x dx, and then this guy converts to cosines like that because it's not sine squared, it's just sine to an odd power, sine to the first. So now we'd be integrating this, and if you let u equal cosine, your integral would ultimately be something like that, and that's not at all straightforward to integrate. So we need a new strategy for situations where we initially start with an even power of sine or cosine. And there's a great solution, which is to use a particular trigonometric identity that you probably don't use a lot, but we're going to start using it a great deal. So let's recall from trigonometry class that sine squared of an angle is 1/2 times 1 minus cosine of twice that angle. And for that matter, cosine squared of an angle is 1/2 1 plus cosine of twice that angle. So these identities are definitely worth knowing because they are going to help us through all these little ones where reserving a factor isn't going to work. So if you're wondering where these came from, or you might be thinking, hey, I took trigonometry, I don't remember those identities. Yeah, well, they don't show up that much. They did make an appearance in your trigonometry class, but you probably saw them as half-angle identities. For instance, you probably saw that sine of an angle a over 2 is equal to plus or minus the square root of 1 minus cosine of a, all divided by 2. And similarly, cosine of a over 2 is plus or minus the square root of 1 plus cosine of a, all over 2. And that's typically how they're presented in a trigonometry class, and they're called half-angle identities in that context. In fact, it's because of where these come from that it's common for people just to refer to these identities as they are here as half-angle identities. So I might even do that a few times. Okay, so how's that going to help us actually solve this problem? Well, here's the original problem. Well, we can simply write this as the integral of 1/2 1 minus cosine of 2x dx. And distributing the 1/2, we will get 1/2 minus 1/2 cosine of 2x dx. Now, I'm going to start using a really helpful shortcut for little integrals like this. This term right here technically would need a u substitution. Okay, let's just for a second integrate cosine of 2x dx. Because this is more than just cosine of a single variable, we would actually need a u substitution here. U equal 2x, du equal 2dx, and so dx would be du over 2, giving us the integral of cosine u times du over 2. And that would, of course, integrate to sine. So we get 1/2 sine of u, and u being 2x, plus c. Now, if you're about to do a u substitution, and the u is just a number times x, like 2x or 7x, you can just integrate directly and divide your answer by that coefficient. So, for example, if we're integrating e to the negative 7x, we can just say, well, antiderivative of e to the stuff is e to the stuff, so e to the negative 7x, and we'll just divide by negative 7. And it's like we did the u substitution. That's a power move that saves a great deal of time in writing, and I'm going to start using that more and more this semester as we go through these problems, so that we're not stopping to do tiny little u substitutions when we can easily predict what the result will look like. Again, this only applies if the u substitution is a constant times x. If it's anything else, you should go and do the full substitution. So why am I bringing that up here? Well, because we have cosine of 2x, not just cosine of x. So with that in mind, we can integrate each term of this integral, and so we get 1/2 x minus 1/2, which is just that number 1/2 right there, multiplied by the antiderivative of cosine 2x. Well, we know that's sine of 2x divided by 2. Again, that divided by 2 part comes from the coefficient, and it's like we quickly did a u substitution without writing anything down. I hope you can appreciate how that's going to save us time in a section like this. All right, let's plug in our points here. So we have, plugging pi in, we get pi over 2 minus 1/4 of sine of 2 pi. And plugging 0 in, we get 0 over 2 minus 1/4 sine of 2 times 0. Well, pretty much everything goes away except for the pi over 2, which is our final answer. All right, here we are with an even power of cosine, which means if we try to reserve a cosine of 6x, that'll leave us with a cosine cubed of 6x, and that's just not very easy to convert over to sines using a Pythagorean identity. So that whole method that we used for the first two examples is just not going to apply here. No problem. We know how to handle these even powers of sine or cosine using the, quote, half angle identity, unquote. So let's use that. Cosine squared of an angle is 1/2 1 plus cosine of twice that angle. Okay. So what do we've got here? This is the original, cosine to the 4th of 6x dx. Well, that's equal to the square of cosine squared. So the cosine squared on the inside can be converted using the half angle identity. So this is going to be 1/2 1 plus cosine of double 6x, that would be 12x. And that entire thing is being squared. Okay, let's clean this up a little bit. We have 1/4, because that's 1/2 being squared, and then 1 plus cosine of 12x being squared. So, of course, we're going to have to FOIL out this binomial. So we're going to get 1/4 times 1 plus 2 cosine of 12x plus the square of cosine of 12x. That would be cosine squared 12x. And let's distribute the 1/4. So we have 1/4 plus 1/2 cosine of 12x plus 1/4 cosine squared of 12x. Okay, so let's just look at each term and see if we can integrate it. 1/4, yes, we can certainly integrate that. 1/2 cosine 12x, Absolutely, right? We would just turn that into a sine. We divide by 12 at the end, and we're good with that one. 1/4 cosine squared. Well, that squared is troublesome, but we can use the identity again to just unwrap that one more time into a cosine of 24x. So I guess we'll have to do that. So the cosine squared becomes 1/2 of 1 plus cosine double the 12x to 24x. All right, so what have we got here? 1/4 plus 1/8 is 3/8 plus 1/2 cosine of 12x plus, and distributing that 1/8 is 1/8 cosine of 24x. And we can integrate 3/8. We can integrate 1/2 cosine of stuff. We can integrate 1/8 cosine of other stuff. So we're good. Let's integrate this thing. This becomes 3/8 x plus, now remember, antiderivative of cosine is sine, but we have 12x, so we know that we're really doing a quick u substitution, which will result in just dividing that whole term by 12. So this is going to be 1/24 sine of 12x. And the same thing here, we are going to divide our term over here by 24. So 8/24s, well, 8/25s is 200. That's 8 too many. So I guess 192 sine of 24x. And our constant. So victory is ours.
To victory! To victory!
Okay, let's summarize the technique that we've seen so far. So basically what we've been talking about is integrating a product of sine and cosine factors, and we'll say sine is raised to the m and cosine is raised to the n. And depending on whether m or n are odd or even, we go down a particular path when approaching the problem. So if either m or n are odd, we can do the thing we were doing where we simply reserve a factor and convert what's left, which would be an even power that's left, easily converting using a Pythagorean identity. Then we would finish with our u substitution. So in the case where both m and n are even, well, that's when we use the half-angle identities. Okay, one thing that's nice is that those identities are so similar. The only difference is the minus and the plus. And I think it's quite nice that for once cosine has like the positive thing and sine gets the negative one, right? It's sort of, in the universe of trig functions, it's always like sine is Mario and cosine is Luigi. And when it comes to these identities, it's like cosine's kind of the main one, right? Sine's the other one. I like that. All right, so we're not going to solve this one completely, but let's talk about how we would approach this. So, well, we only have even powers, right? So we won't have any success by reserving a factor and doing a substitution. So we're going to have to just use repeated application of the half-angle identities. And there actually is a better way than that, but I want to just point out that you could do that, right? This would work. So we could say, well, this is 1/2 of 1 plus cosine of 2x times 1/2 1 minus cosine of 2x. And then you have this big FOIL party, and you'll end up with a cosine squared of 2x after foiling, and one more application of the half-angle identity, and you're good to go. I just want to remind you that there's one more trig identity
But what if I told you there's one more out there?
So if we have cosine and sine to the same power as we do here, and this would work if they're both cubed, if they're both to the fifth power or whatever, there is a quick shortcut here, and that is recalling that sine of 2x is 2 times sine of x cosine of x, the double angle identity for sine, which is wonderful. It's very easy to remember, and there it is. So specifically, that means that sine of x times cosine of x is equal to sine of 2x over 2. So this original integral, which we could write as cosine of x times sine of x all squared, is really the square of sine of 2x over 2, simply using the double angle identity for sine. And that would, of course, be, if we cleaned it up, 1/4 sine squared of 2x. And now we have, an even power of sine, so we'll use the half angle identity as it's prescribed by the method that we just wrote down. And we'd be able to finish this problem, and it'd be a lot easier than what we were about to do by applying those identities directly to the original version of this problem. So that would be the sine double angle identity coming to the rescue, and it's great to pull out when you have cosine and sine together raised to the same power like we do right here. So, bueno. Okay, yeah. Here we have different functions besides sine and cosine finally. Tangent to the 6th power, secant to the 4th power. So the basic principles about reserving factors with dx with the intention of letting u equal something is exactly how we're going to approach even when we've got tangents and secants. So the way we're going to approach this one is by reserving a secant squared to go with our dx. So we have tangent to the 6th power multiplied by secant squared multiplied by secant squared dx. And this is our reserve for du. Now think about, if we're reserving secant squared dx for du, what are we planning on letting u equal in a substitution?
Tan.
Which means that all of that stuff needs to be converted in terms of tangent. Well, perfect. Secant squared easily converts into tangents. So we're going to have tangent to the 6th multiplied by secant squared, which is 1 plus tangent squared, right? I tan secretly. And there's our secant squared x dx. And now we can perform our u substitution. So we'll let u equal tangent of x. So du is secant squared x dx. It's perfectly set up for this. So our integral becomes u to the 6th multiplied by 1 plus u squared and du. All right. So distributing and integrating. The rest is just simple mechanics, right? And what was u? U is equal to tangent. So this is 1 over 7 tangent to the 7. 1 over 9 tangent to the 9. Plus our constant. And we're done. So I will note that we did need to have secant originally to an even power for this to work, because we had to reserve secant squared, and since secant was raised to an even power, when we pull 2 of them out, we still have an even power left, which we can easily convert into tangents. If we had an odd power of secant, then we would have to do something else. All right, with this one, unlike the last example, we will not be able to reserve a secant squared, because that would leave us with a 5th power of secant, and that's not at all easy to convert into tangents. So reserving secant squared with the intention of letting u equal tangent would probably be very difficult. So what are some other options here? Well, what if we intended to let u equal secant instead? But then we would need a secant times tangent for our d theta. So let's see what happens if we manufacture that. So let's rewrite this as tangent to the 4th theta, secant to the 6th theta, multiplied by secant tangent d theta. So this is our reserved for du part, which means our intention is to let u equal secant of theta, so that du is secant times tangent. And that means that since our intention is to let u be secant, that all of that stuff over here has to be somehow converted to secants. No problem, because we have tangent to an even power at this point, which is easy to convert using a Pythagorean identity. So, all right, well, that's tangent to the 4th power, so let's first write it as tangent squared, which itself is squared. Secant to the 6th power, that's already in terms of secant, so we'll just leave it alone. And we have our reserved part here. Okay, so tangent of theta. Now be careful with these Pythagorean identities. This one in particular is secant squared minus 1. And that whole quantity is being squared. All right, so we're ready for our substitution. We'll let u equal secant of theta. So du is secant theta tangent theta d theta, as we predicted, giving the integral u squared minus 1, which itself is squared, times u to the 6th times du. Okay, so now let's just have a FOIL party here. U to the 4 minus 2u squared plus 1, u to the 6th du. Let's distribute that u to the 6th. So we get u to the 10 minus 2u to the 8 plus u to the 6. And we can integrate, it's just a polynomial. So this would be 1 over 11 u to the 11 minus 2 over 9 u to the 9 plus 1 over 7 u to the 7 plus c. And what was u equal to but secant, wasn't it? So this is 1 over 11 secant to the 11 of theta minus 2 over 9 secant to the 9 of theta plus 1 over 7 secant to the 7 of theta plus our constant. Final answer. So what did we need in the original problem for this to work? Well, once we'd reserved the secant tangent, we needed an even power of tangent to convert to secants, which means the original problem needed to have an odd power of tangent. So if you have an odd power of tangent, then your intention should be to reserve secant tangent and let u equal secant. This is probably getting confusing, so let's write down everything we've learned so far when it comes to tangent and secant. Okay, so let's summarize here. To integrate, say, tangent raised to the mth power multiplied by secant raised to the nth power. Well, let's see. If m is odd, as it was in the last example, then reserve secant x tangent x dx and rewrite what's left in terms of secant x, right? So once you reserve a secant times tangent, you'll have an even power of tangent left, which easily converts into secants, and then the substitution will be let u equal secant of x. Okay, if n is even, then we'll reserve secant squared of x dx. This was 2 examples ago. Okay, so reserving that secant squared, we'll leave an even power of secants because n was even to begin with, which easily will convert over into tangents. And at that point, we'll let u equal tangent of x. All right, unlike the case where we were dealing with multiples of sine and cosine, this method is not comprehensive. It does not handle the case where m is even and at the same time n is odd. So if we have an even power of tangents and odd power of secants, well, things start to get interesting. And the best way to handle that, in my experience, is to use integration by parts. So if you have an even power of tangents and an odd power of secants, then consider using integration by parts, letting u equal everything but secant squared and reserving that secant squared to go into dv for your integration by parts, which easily will integrate into tangent, and so your new integral will consist of a tangent factor multiplied by the derivative of whatever's left that you put into u. Let's see an example of this process. Okay, so here we have an odd power of secant and an even power of tangent. Well, that's a power of 0 because tangent's not even present, but 0 is still even. The suggestion is to use integration by parts. And what we're going to do for integration by parts is we're going to let u be everything except for secant squared, which we're saving for dv. So that means our u is going to be secant of x, and our du will be the derivative of that, which is secant of x tangent of x dx. Our dv is secant squared dx, and our v is the antiderivative of that, which is tangent of x. So our integral becomes ultraviolet voodoo. U times v is secant of x tangent of x minus v du. Well, that would be secant of x times tangent squared of x. Okay, well, we have a new integral here that we've punted to, and hopefully it's better than the one we just started with. Well, let's see. We have an odd power of secant. That's not great. And we have an even power of tangent. That's also not great. So the suggestion would be to use integration by parts and reserve secant squared, but we don't even have a secant squared now. Okay, well, in this case, we can get a little creative and rewrite the tangent squared as secant squared minus 1. So what we really have is this is equal to secant of x tangent of x minus the integral of secant of x times secant squared of x minus 1. Okay, for some of these gnarly ones, sometimes you just have to play around until something works. Distributing the secant, we have secant cubed of x minus secant of x dx. All right, so now let's look at our pieces. Can we integrate secant cubed? Well, that's familiar. That's the actual integral we're working on right now. But that's good. It means we can just move it to the other side. The boomerang method, right? And solve for the integral of secant cubed. Okay, but what about the secant of x? Can we integrate secant of x? Well, indeed we can. That was one of the first things we did at the beginning of this lecture. So what are we dealing with here? Secant of x tangent of x minus the integral of secant cubed of x dx, and plus, by distributing that negative, integral of secant of x dx. So if we add to the other side, we get 2 times the integral of secant cubed is equal to this. Okay, well, we know the integral of secant is ln of absolute value of secant of x plus tangent of x. And so all we have to do to finish this problem is divide everything by 2, and of course we'll add our constant. So we get, therefore, the antiderivative of secant cubed is 1/2 secant x tangent x plus 1/2 ln of absolute value of secant x tangent x plus c. And that's our final answer. Okay, for this last example, we have a completely different type of problem. The issue here is that the arguments are different. We have sine of 3 theta and cosine of 2 theta. And that creates a lot of problems for any of the techniques that we've seen so far today. So our first job should be to find a way to get those all down to the same. So how can we do that? Well, we know what to do with cosine of 2 theta, because cosine of 2 theta, there's an identity where that's just cosine squared theta minus sine squared theta. And all we have to do is find some identity to turn sine of 3 theta into cosines of thetas and sines of theta. And then we'd have this big mess of cosines of thetas and sines of thetas, which we could manage, right? We know how to handle a big mess of cosines and sines of theta based on like the first half of this lecture. The problem is, does anyone know a triple angle identity for sine? Probably didn't learn one in trigonometry, right? So, well, you could invent one. Let's invent a triple angle identity for sine. So we could say, well, sine of 3 theta, that's like sine of 2 theta plus theta. Okay, so what is that? Well, sine of one thing plus another, we know there's the sum and difference identities for sine. So this would be sine of the first thing, cosine of the second thing, plus cosine of the first thing, sine of the second thing, sine, cosine, cosine, sine. And now we can say, oh, well, sine of 2 theta is 2 sine theta cosine theta. So that would be cosine squared at this point. And over here we have cosine of 2 theta, which is cosine squared minus sine squared times sine of theta. And now we have a whole bunch of sines and cosines. But the thing is they're all on the same argument. They're all theta. And when we bring that up and multiply by cosine of 2 theta, when it's converted to cosine squared minus sine squared, we will have our big happy mess of cosines and sines that we can integrate, right? Okay, that will work, but that is a very inefficient way of approaching this problem. I went into that simply to demonstrate that with enough grit, you can create an identity for just about anything that you need, but it could create a lot of work for yourself. So what is the best way to approach this? Well, one more identity, and this one you probably have not worked with at all. So we're going to use this identity here. Sine of A times cosine of B is equal to 1/2 sine of A minus B plus sine of A plus B. And you would be completely forgiven if you've never seen that before. So it's not even one that I have memorized because I use it so infrequently. If I were to put a problem on a quiz or an exam that required that identity, I would say right in the problem, use this identity right here, and I'd give you the identity. Okay? So, all right, well, how do we use it? Well, I think it's clear that here in this example, our A is 3 theta, and our B is 2 theta. So our integral becomes 1/2 sine of A minus B, that's 3 theta minus 2 theta, plus sine of A plus B, 3 theta plus 2 theta. So that would be 1/2 of sine of theta plus sine of 5 theta. And while we still have two different arguments, it's not a problem because this is actually like two different integrals. We could distribute the integral across a sum. So we have the integral of 1/2 sine theta plus a completely different integral, 1/2 sine of 5 theta. And this is very easy to work out. Antiderivative of sine is negative cosine, so this is negative 1/2 cosine of theta. And over here, same thing, except we're also going to divide by 5. So negative 1/10 cosine of 5 theta, plus our constant. And we are done. So I think there's no contest. That particular identity is exactly what you would want for a situation where you have a product of trig functions and they have different arguments.